Hello everyone, my name is Wei Chi and today I'm going to present our work about the flexible partial MDS codes. Our group comes from the Center of Pervasive Communications and Computing. We are in University of California, Irvine. So in this presentation, I will first introduce the background and contributions and then explain the detailed constructions and next we introduce a little bit about the extensions based on our work. Let me first introduce a little bit about the background. So data storage is a critical problem for long volatile memories. And the popular approach to this kind of challenges is that using MDS code. MDS code means that we can encode the information symbols into a number of storage nodes. And from any K of it, we can recover the whole messages. But nowadays, we are applying SSD and it brings on new challenges. Sometimes we need to face a mixed type of failures, which containing the load failures and the symbol failures. As you can see in this picture, the node failures means that the whole node is failed and we cannot access to any of the symbols in this node. And symbol failures means that only part of the symbol is failed in this node, and we can still access to the rest of symbols. Partial MDS code is introduced for this kind of challenges. It can face and overcome the mixed type of failures that containing the load failures and additionally symbol failures. However, for the partial MDS code, it is designed for a given redundancy level. That means that it can only make use of the K nodes. And in this case, the rest nodes are wasted and each node needs to downloading all the symbols, which will result in a larger latency. As you can see this picture, so the partial MDS code is designed for 5 nodes and the reconstruction parameter K is equal to 3. It can tolerate at most 2 node failures. However, when there is only 1 node failure, we can still only make use of the 3 nodes and there will be 1 node wasted. So in this case, all the symbols are downloading from the 3 available nodes, which will result in a bigger latency. To overcome this kind of questions, we provide a flexible partial MDS code in our work. Table 1 is example when we have a number of nodes equal to 5 and the reconstruction parameter equals to 3. And each node is containing 4 symbols and we can tolerate 2 additionally symbol failures. So here we can adjusting our reconstruction parameters K to be 3 or 4 according to the number of failures we have. And here L means the number of symbols we accessed in each node. For example, assume we have 2 node failures. In this table, the star means a node means the failures have 2 node failures and 2 additionally symbol failures. In this case, we can only access 3 available nodes and we need to access all the 4 symbols in the available nodes. In this case, we can still recover the whole messages. Or alternatively, in some cases, we only have 1 failure. In this case, the node 5 is failed and we also have 2 additionally symbol failures. In this case, we only need to download 3 symbols each node. That is the first 3 symbols each node. In this case, we can still download 10 symbols, which is good enough for us to reconstruct our messages. Here are some related works. The partial MDS code was first introduced in 2013 by Blum. And in 2016, Collis and Colquhoun introduced a general construction for all the parameters. And later in 2019, Gabres and others provided a construction for partial MDS code that can be applied for the smaller fields. And in the recent work, Blum also introduced a hierarchy architecture that can tolerate different number of symbol failures in different layers. Next, I'll introduce a little bit about the constructions of our work. So this work is based on the college work in 2016. It provides a general construction for partial MDS code. In the encoding, we have two steps. In the first step, we encode the original information to the copy during code word symbols. So, and in the second step, we encode the copy during code word symbols into MDS code in each layer. As you can see in the table, the code word symbols with a white background are the copy during code word symbols. And here, each symbol is a scanner that containing several symbols. And also for the gray part, it is the parodies that encoded from the MDS code word in each layer. Here we can see that in each layer we have a different reconstruction parameters k, and in this case we can adjusting our reconstruction parameters according to the number of failures. For example, if you only have n minus k1 failures, we only need to access to layer 1 each node. And if we have n minus k2 failures, we need to access the layer 1 and layer 2 in our code. And in the worst case, when we have n minus ka failures, we access all the symbols in the available nodes. And in this case, we can still recover the whole messages. So this work is based on the college work in 2016. And in the case when we have only one layer, it is the same, it is the exact construction of the college work. Next, let me introduce a little bit about our parameters. So n is the number of nodes and k is the reconstruction parameter. So L means that the number of symbols in each node, and we set KL equals to K1 L1 equals to K2 L2 equals to KA LA. It means that no matter which layers we have accessed, no matter how many failures we have, the total number of symbols we access remains the same. And we also define S as the number of additionally symbol failures. In the next page, I will present a detailed construction for our code. We present the vector form of each code word symbols. Here, we divide our code construction into A layers, and layer J is the LJ minus 1 plus 1 row to the LJth row. For example, layer 1 contains the row 1 to row L1, and layer A contains the last LA minus LA minus 1 rows. We also have three indexes to expand the location of each code word symbols. The first index is J, which is a layer index. It means that in which layer is the code word symbol located. The second parameter is MJ. It means the row index, means that after we know which layer is the code word symbol located, we need to decide in which row are these code word symbol located. And the last index is I, which means that in which node is the code word symbol located. For example, we can look at the C122 here. It means that the code word symbol is located in the layer 1. And it's located in the second row of layer 1. And it is located in the node 2. Next, I'll explain more details about our encoding and decoding function. So the first step is that we encode our original information to the copy during code word symbols. As I have explained before, we totally access k times l information symbols in all the available nodes. And consider that we have s additionally symbol failures. So the total number of original information symbols is at most KL minus S. We define it as a capital K. And in the first step, we need to encode all the information symbols into the copy during code word symbols. So here, the number of copy during code word symbols is the sum of Kj times Lj minus Lj minus 1. So Kj is the reconstruction parameter, or to say dimensions of each layer, and Lj minus Lj minus 1 is the number of symbols for each node in this layer. So after we get the Gabby-Doodling word symbols, the next step is that we need to encode them into the MDS code. So here, as we can see, the right side of the equation. So column 1 to column Kj are the Gabby-Doodling word symbols, and column Kj plus 1 to column K to column N are the parities for the MDS code. So G here is the encoding matrix. By doing so, we have encode all our code word symbols. Next, I'll give a specific example and explain how it is encoded. So this example with 5 nodes and reconstruction parameters equal to 3 means that we can tolerate at most 2 node failures. And 4 means that each node will have 4 symbols, and 2 is the number of additionally symbol failures we can tolerate. So in the first step, we encode the 10 information symbols into 15 Gabby-Doodling code word symbols. In this case, the code word symbols with the white background are the Gabby-Doodling code word symbols, and the code word symbols with the gray background are the parities of the MDS codes. So you can see that in row 1, row 2, and row 3, we have an MDS code with reconstruction parameters of 4. We only have 1 parities. And in row 4, we apply a 5-3 MDS code. Means that in the last row, we can recover all the code word symbols from any of the 3 symbols. So by doing so, we have 2 layers, and the layer 1 is K1 equals to 4. Means that if you have 4 available nodes, we only need to access 3 symbols in each node. And in the second parameter, we have K2 equals to 3. Means that if you have 2 node failures, we can still decode all the messages by downloading all the 4 symbols in each available node. So now I have introduced about our encoding function. Next, I'll introduce about how we decode. We assume that we have n minus kj node failures and s additionally symbol failures. It means that we have at most we have kj available nodes. So the first step is that we decode the Gabby-Doodling code word symbols from our MDS code. We define that TMJ is the number of symbols we can download in each row. Definitely this should smaller or equal to kj because we totally have kj available nodes. And since considering we have s additionally symbol failures, the total number of symbols we can download is Lj times kj minus s. And in this case, it is the exact number of the K Gabby-Doodling code word symbols. And using the MDS property, we can decode all of these Gabby-Doodling code word symbols. The next step is a little bit quite straightforward. After we get all the Gabby-Doodling code word symbols, we can decode the originally informations from the decoding of Gabby-Doodling code word symbols. Next, I will present a detailed example about how we can decode the original information symbols. This is an example with the same parameters as the previous examples. So in this case, we have 1 node failures and 2 additionally symbol failures. As I've explained before, in this case, we can access 4 available nodes, and each node will need to access 3 symbols. That is row 1, row 2, and row 3. So as you can see, we read 3 symbols in row 1, 4 symbols in row 2, and 3 symbols in row 3. In this case, we get 10 symbols, and they are exactly the Gabby-Doodling code word symbols. So from these 10 Gabby-Doodling code word symbols, we definitely can decode all the messages. And in the second example, we have two node failures and two additionally symbol failures. In this case, we only have three available nodes, and we need to download all the four symbols in the three available nodes. As you can see here, in the first node, we download four symbols. In the third node, we download three symbols, and in the fourth row, also download three symbols. So the symbols in the first three, they are exactly Gaussian code, but in the last row, the C214 here is a parity. But we know that in row 4, it is a 5-3 MDS code. So from these three symbols, definitely we can decode C212 here, which is also a Gaussian code word symbols. So totally, we can still decode the 10 Gaussian code word symbols. And in this case, we can still decode our originally information symbols. Next, I will show how good is our code with related to performance. So in this case, we assume that we have 15 nodes, and each node have a failure probability of p equals to 0.2. And downloading one symbol takes time t. So here we can use a fixed partial MDS code. For example, we can set k equals to 8. That means that if we have at least 8 nodes, then we can decode all the information symbols. So by doing so, we can have a high probability of successfully decoding all the messages, which is equal to 99%. And in this case, since we need to downloading all the symbols in each node, we have an average latency of 15 times t. And alternatively, we can set the fixed RGMDS code with the k equals to 10. In this case, the probability of successfully decoding all the messages is about 94%. But in this case, we're only downloading 12 symbols in each node, which causes an average latency of 12 times t. Or we can also set the k equals to 12. So in this case, we only need to download 10 symbols in each node, which have an average latency of 10 times t. But in this case, the probability of successfully downloading all the messages is really low. It only has about 65%. So alternatively, we can apply our partial MDS code constructions. So in this case, we have three layers. The first layer is k1 equals to 12 and l1 equals to 10. And the second layer is k equals to 10 and l equals to 12. And third layer is k equals to 8 and l equals to 15. So in this case, if we have 12 available nodes, we only need to download 10 symbols in each node. And if we have 10 available nodes, we need to download 12 symbols in each node. And in the worst case, if we only have 8 available nodes, then we need to downloading all the 15 symbols in each node. In this case, we can see that we can have the maximal failure tolerance. So the probability of we can successfully decoding all the messages is 99%. And also, since in most cases, we have more available nodes in the worst case, we don't need to download all the symbols in each node, so we can save the average latency. The average latency for our flexible partial MDS code is 10.82 times t. So you can see that in this example, we're maintaining the maximum failure tolerance, but also we can reduce the average latency because we don't need to download all the symbols in each node in most cases. Okay, next I'll introduce a little bit about our extension works. So for this kind of like construction, it can be also applied to MDS code. And it is quite similar to the partial MDS code. And we're also looking at the optimal repair property for this kind of like, for this MDS codes. And also the locally recoverable codes are also interesting. It can all be applied to our construction. And by doing so, we can maintain the locality properties for the locally recoverable codes And also we can maintain a flexible probability, which we can recover the whole messages from a flexible number of nodes according to the failures we have. Yeah, that's all about our work for the partial for the flexible partial MDS codes. Thanks.